Today, we're diving into the chemical and spectroscopic analysis of 3I, Atlas. This is the story of a really fascinating object, a visitor from another star system with a chemical makeup that's, well, unlike anything we've seen before. Let's break down what the science says.
This analysis was brought to us by Orchid, who is the corresponding author, and Abhay Shamala. And there's a really important note right at the top here from the researchers. This publication is based on current observations, and ongoing studies might refine or even revise some of these findings. So this is science in action as it happens. So here's how we're going to tackle this. First, we'll talk about how this thing was discovered and how we studied it. Then we'll get into the juicy details of its chemical makeup. After that, we'll look at its physical properties, see how scientists modeled its weird activity, and then we'll put it all into context to see what it all means. And finally, we'll wrap up with the big conclusions and what's next for this interstellar traveler.
All right, let's jump right in. We're starting with the introduction and the observational approach. This is all about how we found this object and the incredible worldwide effort it took to get a good look at it. Okay, so what is 3I/Atlas, and why is it such a huge deal? Well, for starters, it's only the third confirmed object we've ever seen that's come from another star system. And get this, it's the first one that the James Webb Space Telescope was able to characterize before it swung around the sun. But the real kicker was its behavior. It started to get active, releasing gas, way out at 5.1 AU from the sun. That's a distance where things are usually frozen solid. This completely unexpected activity kicked off a massive observing campaign to figure out what was going on. And when I say massive campaign, I mean it. We're talking about the heavy hitters of astronomy. The James Webb Space Telescope used its powerful infrared eyes, NIRSpec and MIRI. Down in Chile, the Very Large Telescope pointed its X-shooter and UVEST spectrographs at it. In France, the NOEMA radio telescope array listened in at millimeter wavelengths. And of course, the Hubble Space Telescope gave us some critical images in the ultraviolet. It was a truly global, multi-wavelength effort. So, with all these amazing telescopes pointed at it, what did we actually find? Let's dig into the comet's chemical makeup. We're talking everything from familiar ices to some really strange metallic gases. This table really shows the chemical cocktail this comet was serving up. JWST saw it was releasing a ton of water, about 1.2 times 10 to the 26 molecules every single second. But it was also kicking out a lot of carbon dioxide, about a quarter of the amount of water. And on top of that, the NOEMA telescope found carbon monoxide at about 4% of the water's rate. It's this specific mix of ices that really starts to set 3I Atlas apart. But it wasn't just about those big three. The VLT also spotted cyanogen, or CN. And this is where things get even weirder. As the comet got closer to the sun, the amount of CN just shot up, way faster than what we see with comets from our own solar system. This suggests the CN wasn't coming directly from the nucleus, but maybe from the dust grains in its coma. At the same time, other carbon molecules we expected to see, like C2 and C3, were nowhere to be found. That's a huge difference compared to the last interstellar comet, 2I/Borisov. Now, the chemistry just gets stranger when we look at the metals. The VLT found 22 distinct signatures of nickel gas, but incredibly, no sign of iron. That means this comet has a nickel-to-iron ratio that's more than 160 times higher than our sun's. So, where's all this nickel coming from without any iron? Well, the leading theory is that sunlight is breaking apart a molecule called nickel carbonyl, which would release nickel atoms without needing any iron. It's a really wild chemical puzzle. Okay, let's shift gears a bit. We've talked about the gas. Now let's look at this solid stuff, the dust and the building blocks of the comet itself. We're going to check out its isotopic and physical properties to hunt for clues about where it came from. This slide highlights two really critical discoveries. First, on the left, you see the isotopic ratios. The mix of different kinds of carbon and oxygen atoms is almost identical to what we find right here in our own solar system. This is a huge deal. It suggests the fundamental building blocks for planets might be pretty common in our galactic neighborhood. Then, on the right, we have the dust mineralogy. JWST found that the dust is mostly made of amorphous silicates, basically glassy non-crystalline minerals. The fact that we don't see crystalline silicates, which form at high temperatures, tells us this material has been kept incredibly cold for its entire life. So what's this dust actually like? Well, it reflects light with a reddish tinge, and the way it scatters that light points to it being made of fluffy, porous clumps.
Think cosmic dust bunnies. On top of that, data from the Liverpool telescope showed that the light bouncing off the dust is highly polarized. That's a dead giveaway that the dust grains aren't just porous, but they're also packed with carbon. So we have all of these observations, all these different pieces of the puzzle. The next big step is to build and model that can explain it all. So this next section is all about the thermal modeling that ties this whole incredible story together. So how do we explain why this comet turned on so early? Well, researchers put together a thermal model to figure out exactly when the carbon dioxide ice on its surface should start to sublimate, turn directly into a gas. The model predicted this would kick off when the surface hit about 65 Kelvin, which would happen at a distance of 5.1 AU from the sun. That's a perfect match for what they actually saw. The model was even able to reproduce the amount of gas they measured, just by assuming that only a tiny 4% of the comet's sunny side was actively spewing out gas. It all just clicks. Okay, so let's pull back and look at the bigger picture. What does 3I/Atlas really tell us about the population of interstellar objects out there? And, just as importantly, what can this discovery teach us about how we talk about science in today's world? When you put our 3 confirmed interstellar visitors next to each other, you see this amazing pattern emerge. 1I/Oumuamua was very dry, almost like a rocky asteroid. 2I/Borisov was on the other extreme, super rich in carbon monoxide. And 3I/Atlas, it sits right in the middle, rich in water but with a healthy dose of carbon dioxide. And the fact that both interstellar comets, Borisov and Atlas, have that bizarre nickel-to-iron ratio, that points to some kind of common mechanism for how metals get released from these objects. This discovery also gave us a masterclass in a very modern challenge: misinformation. Within just 48 hours of the CO₂ detection being announced, a staggering 62% of over 1 million social media posts were talking about alien greenhouse gases. But this light also shows a powerful tool against that. An AI classifier called AstroBert V2 was able to slash the half-life of this misinformation from 28 hours down to just 6, all by automatically linking people back to the actual scientific data. It's a fascinating look at the new frontier of science communication. And all of that brings us to the end of our journey today. Let's summarize the key findings from this incredible object and take a quick look at what's on the horizon. So, to wrap it all up, 3I/Atlas is the first interstellar comet where we can measure both water and CO₂, and it beautifully bridges the gap between our previous 2 visitors, Oumuamua and Borisov. It's got a high CO₂ to water ratio, that wild overabundance of nickel, a strange lack of carbon chain molecules, and it's built from cold, glassy silicates and fluffy, carbon-rich dust. But for all its weirdness, its basic isotopic building blocks look just like ours. The story is far from over. Future observations with JWST and Oumuamua are going to dig even deeper, trying to unlock even more of its chemical secrets. What an incredible object, and what a story it still has to tell. For anyone who wants to go even deeper, the next few slides contain the full list of references cited in this work. We'll continue here with the next set of publications that this research was built on.
And here is the next group of references for your review.
Here are more of the papers and data sources that informed this analysis. And this is the final list of references. Thank you so much for joining us for this deep dive into the fascinating world of 3I/Atlas.